Hello, now I'm going to discuss the standing waves or the stationary waves in history. Now to understand standing waves, we need to understand what is progressive wave. A progressive wave is a wave which travels continuously in a medium in the same direction without changing amplitude. That means the wave is progressing in a specific direction. That's why they are called as progressive wave. Now comes what is stationary waves, or how can you produce stationary waves. Now stationary waves can be produced when two progressive waves of same amplitude and wavelength traveling along a straight line in opposite directions superimpose on each other. So when we have got two progressive waves traveling in opposite direction and they have the same amplitude and wavelength, if they superimpose, then stationary waves are produced. Now the stationary waves can undergo reflection and transmission. So during the reflection, when the wave strikes a boundary and come back, this is called as reflection. And transmission is when the wave passes from one medium to another medium. This is called as transmission of wave. Now this is the diagram of how a wave can behave in case of reflection. For example, this is an incident wave traveling with velocity v in this direction. So the incident wave is represented by this equation yi is equal to a sine omega t minus kx. It is striking at the boundary. After striking, it is returning back with velocity v in opposite direction. So you can see as it is returning back, its amplitude is changing sign because there is a phase change of 180 degree. Earlier the wave is like this, now the wave is just opposite like this. So there is a change in phase, therefore the amplitude is minus. And there is a change in direction of the wave. Earlier the wave was going in this direction, now the wave is going in this direction. So there is a change in direction of the wave also, therefore this minus sign is becoming plus. So this is called as the reflection from a fixed end. So this end of the string is fixed. Now I can show you one animation regarding how the wave is undergoing reflection from fixed end. Next I will show you how the wave undergoes reflection from free end. You can see this end is free. This is like a ring, and as the wave is traveling in this direction, it undergoes reflection from this free end and it is returning back. In this case, there is no change in phase. You can see the direction of this amplitude is here in case of incident wave, and in case of reflected wave also the direction of amplitude is here only. That means there is no change in phase, only there is a change in direction. So now for better understanding, you can see this animation. This animation will show you how the wave undergoes reflection from free end and fixed end. We will be looking into the free end. Here you can see a string whose one end is fixed. So, and this end is free. So as the wave is moving from the free end to the fixed end, after striking at the fixed end, it is undergoing a change in phase because the amplitude of this wave is changing sign. You can see this is the reflected wave. This red one is the reflected wave. Again you can see the wave, the white one represents the wave is incident wave. The white one represents the incident wave moving towards the fixed end. After getting reflected from the fixed end, you can see it undergoes a phase change of 180 degree. It is changing its direction. Therefore, this represents the reflected wave whose amplitude changes sign. So in this way, we can understand how the transverse wave undergoes reflection from a fixed wave. Again, you can see the video. This is the white one represents the incident wave and the red one represents the reflected wave. Next, we will be looking into the. So you have understood how the wave is undergoing reflection from the fixed end. Now let's see how the wave is undergoing reflection from free end from this animation. Now you can see the reflection of a string from a free end. This end of the string is free. This is a string. So if we give this string a jerk, how the transverse wave in the string will move. You can see this is the incident wave. It is undergoing reflection, and after reflection, this red one represents the reflected wave. There is no change in phase in the reflected wave, but there is a change in direction of the propagation of the wave. In case of reflection from fixed end, we have seen the direction of the amplitude of this wave changes, but in this case there is no change in the direction of the amplitude. Okay, in this way we can understand the reflection from a free end, the reflection of transverse wave from a free end. Again, you can see the video. This white one represents the incident wave. It is undergoing reflection. And after reflection, this is the reflected wave. So in this way we can understand how the transverse wave undergoes reflection from a free end. Thank you. So you have seen how the wave undergoes reflection from fixed end and free end. Next is transmission of a wave. Now you can see, for example, I have got a wave traveling in this direction. The equation of the incident wave is represented by yi is equal to ai sine omega t minus kx. For example, this is a boundary separating two medium. This one medium, this another medium. So as it is moving towards the second medium, this is another medium. So you can see the transmitted wave has got a different amplitude represented by at, while the direction of the wave is same because the wave is traveling in this direction only. So there is no change in this sign. It is minus only. Here it is minus. Here is minus only. Only there is a change in amplitude of the wave. That is the magnitude of the amplitude will change. So these are the position of the nodes and antinodes in case of a standing waves. So nodes are the position. These are the position of the nodes. You can see, and the distance between two consecutive nodes is lambda by 2. That means from this node to this node, if you subtract lambda minus lambda by 2, you get lambda by 2. Similarly, these are the position of the antinode. You can see these are the position of the antinodes. This top position, they are the position of the antinodes, crest or drop. So the distance between two consecutive antinodes is also equal to lambda by 2. Next, we will be looking into how the harmonics are produced. Now, here you can see the distance between the nodes and the antinode is lambda by 4. So the distance between two nodes is lambda by 2, the distance between two antinodes, consecutive antinodes, is lambda by 2, and the distance between a node and an antinode is lambda by 4. So now let's go into the analytical treatment of standing waves in a string fixed at both ends. So the incident wave is represented by yi is equal to a sine omega t minus kx, the reflected wave is represented by yr is equal to minus a sine omega t plus kx. I already told you there is a change in phase, so therefore negative sign is coming, and there is change in direction of the wave, so a positive sign is coming here. It was negative, it was positive. So after superimposition, y net is equal to y incident plus y reflected. So incident wave plus the reflected wave. So after little trigonometry, if we apply the formula sin A minus sin B, then you will get this. So it is equal to a twice of cos omega t sin minus kx. So after rearranging, minus 2a sin kx cos omega. So this is the net result after superimposition of the incident and the reflected wave. Here you can see this is the amplitude part and this is the phase part. Now we know that at nodes the net displacement of the particle is 0, therefore y net is equal to 0. That means this entire term will be equal to 0 for nodes to be formed. From here you can see sin kx equal to 0, kx equal to 0, pi, 2 pi, 3 pi. When sin kx is equal to 0, then the value of kx will be 0, pi, twice pi, thrice pi, like this. So x equal to 0, pi by k, 2 pi by k, 3 pi by k. So in this way, if you put k is equal to 2 pi by lambda, then the position of the nodes, x represent the position of the nodes, x equal to 0. In place of k, I am writing 2 pi by lambda. In place of k, again 2 pi by lambda, like this. So in this way, x is equal to 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda. So these are the position of the nodes. Next, in general, what you can write, the position of the antinodes as n lambda by 2, where n is equal to 0, 1, 2, 3, like this. The position of the nodes. Now the antinodes are the position where the net displacement of the particle is maximum, or you can say maximum amplitude. So in this case, the same equation, this equation number 1, this same equation, from this equation we see that sin kx equal to 1. So kx will be equal to pi by 2, 3 pi by 2, 5 pi by 2. So these are the from here x equal to this, and putting k as 2 pi by lambda, so we are getting the position of the antinodes as lambda by 4, 3 lambda by 4, 5 lambda by 4, like this. So in general, the position of the antinode is 2n plus 1 lambda by 4. So where n is equal to 0, 1, 2, 3, like this. So next we will be looking into the harmonic structure. Harmonic structure means how will the thing change when n will change. So for first harmonics, let's see like this. So for first harmonics, n is equal to 1. That means the position of the nodes will be x equal to n lambda by 2. You can see here, in general, the general equation for nodes is that you can see the general equation for the nodes. This is the general equation for the position of the nodes, x equal to n lambda by 2. So if n is equal to 1, then x will be equal to lambda by 2. If n is equal to 1, x will be equal to lambda by 2. So that means what? This is the structure of the standing waves produced inside in the string. That means the entire length of the string, x equal to 0 to x equal to L, this is the entire length of the string, is divided into half of wavelength. So L is equal to lambda by 2, this gives lambda is equal to twice of L. Now frequency, we know that V by lambda. So this new one represents the frequency of first harmonic. So in place of lambda, I am putting twice of L, so V by twice of L. So this represents the frequency of the first harmonic, where V represents the velocity of the wave, velocity of the standing wave in the string. Now for second harmonic, that is n is equal to 2, the general equation of node is x equal to n lambda by 2. So for n is equal to 2, we get second harmonic. For n is equal to 2, x equal to lambda. If you put n is equal to 2 here, then x will be equal to lambda. So this is the structure of the standing waves inside of the string when n is equal to 2. That is second harmonic. That means what? The entire length of the string is divided into one wavelength. This is one complete wave or one wavelength. So you know that mu is equal to v by lambda. In place of lambda I am putting L. So the frequency of the second harmonic will be mu 2 is equal to, if you multiply by 2 and divide by 2, you can rearrange this. You multiply 2 here, divide 2 here. So this gives the frequency of the second harmonic. Now you can see v by twice of L is equal to mu 1. I already showed you the frequency of the first harmonic is v by twice of L. So mu 2 is equal to 2 twice of mu 1. This is the frequency of second harmonic. Similarly, the frequency of the third harmonic we can get when n is equal to 3. So putting here n is equal to 3, we get x equal to 3 lambda by 2. This is the structure of the standing waves for third harmonics. That means the entire length of the string is divided into 3 times of lambda by 2. You can see this is one complete lambda and this is lambda by 2. So from here to here it is lambda, and from here to here it is lambda by 2. That means lambda plus lambda by 2 is 3 lambda by 2. So from here we get lambda is equal to 12 by 3. So frequency is equal to v by lambda. In place of lambda I am putting twice of L by 3. Thus we get the frequency of the third harmonic. Mu 3 is equal to 3 times of v by twice of L. Now v by twice of L is the frequency of the first harmonic, as you already know. Therefore the frequency of the third harmonic is equal to 3 times the frequency of first harmonic. So mu 3 is equal to twice of mu 1. So in this way we can get the frequency of the first harmonic, second harmonic and third harmonic. Now let's see the actual animated video of this harmonic structure. Here you can see how the harmonics are produced in a string fixed at both ends. You can see this is a string whose both the ends are fixed. So this is the case when n is equal to 1. That means the case of first harmonic. You can see that the entire length of the string is divided into half of a wavelength. So this is the case of first harmonic. This white one represents the envelope. If I remove this envelope, you can see actual vibration of the string when n is equal to 1. So if I just increase the envelope represents the boundary, actually how much is undergoing, to what extent this string is undergoing displacement. Okay, so this position is x equal to 0, this position is x equal to 0. So if n is equal to, next is if n is equal to 2, then what will happen? Now in case of, you can see this is the case when n is equal to 2. Now you can see when n is equal to 2, then the entire length of the string is converted into one wavelength. So this represents the vibration of the string for second harmonic. Now if you move for n is equal to 3, this is the pattern of vibration. This is the case for n is equal to 3, that is third harmonic. You can see that the entire string is divided into one full wavelength plus one half wavelength. Then if n is equal to 4, that is fourth harmonic, this is the pattern. Okay, this is the pattern of vibration. If n is equal to 5, this is the pattern of vibration. So in this way, you can understand the harmonic structure. So in this way, we have seen how the harmonics structure are when the string is fixed at both ends. Now let's see how the things will change when the string is opened at both ends. Now this one represents the standing waves produced in a string whose both ends are open or whose both ends are free. So this is the shape of n is equal to 1, that is first harmonic. Now if n is equal to 2, it's the shape of the standing waves produced in this field. Similarly, if n is equal to 3, is the shape of the standing wave. You can see at both the ends there are antinodes formed. If n is equal to 4, is the shape, and for n is equal to 5, here. So this is the way by which we can understand the harmonics of standing waves in a string or in a medium whose both ends are free. So I hope you have understood how the standing waves are produced in a string whose both ends are fixed or whose both ends are free. Thank you.